Hi, I'm Laura Sberna. I'm a final year PhD student at Perimeter Institute, and in this talk, I'm going to tell you about white dwarf black hole binaries as a source for the LISA mission. This is work still in preparation done with Alexandre Toubiana from Paris, another final year PhD student, and with Cole Miller. In the title of the talk, we are referring to these white dwarf black hole binaries as exotic binaries for the LISA mission. And this is because really the dominant source for LISA is instead made up of binary white dwarf systems, so white dwarf binaries. These binaries are going to make up a significant noise, background noise for LISA, and around 10,000 of them will also be individually resolvable. But this is really only one of the potential combination of galactic binaries for the LISA mission. And in this work, we want to convince you that also the combination of white dwarf and black holes are interesting targets for LISA, and that their gravitational wave signal is going to be even more informative compared to white dwarf binaries, as I will explain later. These binaries, white dwarf black hole binaries, are going to be necessarily less numerous in the galaxy compared to white dwarf binaries. As you can see from this data from Hurley et al. 2002, these predictions, population predictions, white dwarf black hole binaries are going to be less numerous in about 4 orders of magnitude compared to the main LISA source. However, given that one of the components is going to be a black hole, the SNR is necessarily going to be higher if these systems are observed in the galaxy, since the SNR for the gravitational wave signal is going to go like the chirp mass to the 2/3. And this increases the chances that some of these systems will be visible for LISA. On the electromagnetic observational side, these population, white dwarf black holes, have been quite elusive. There's very limited evidence. One potential candidate is the X-ray binary X9 in 47 Tuk, the globular cluster. But even for this candidate, there's no definite evidence that the two components are indeed the white dwarf and the black hole we're looking for. So this makes our predictions and observations by LISA more uncertain, of course, but at the same time this gives LISA an interesting opportunity to shed light over such an elusive population. So before I go into the details of the potential LISA observations, I will tell you more about exactly what kind of system we have in mind. So what we're going to study is an accreting system where the white dwarf is the donor and the black hole is the accretor. So there's going to be a white dwarf overfilling its Roche lobe, which is symbolized in this plot by the dashed line. And the accretion stream is going to form an accretion disk around the black hole. The accretion rate onto the black hole can in general be higher than the Eddington level, but it's believed that at such high levels the accretion would be unstable, and that the Eddington is really a limit for these systems, that whatever extra would be lost in winds. And accordingly, we assume that the mass transfer is not necessarily conservative, and we cap the accretion onto the black hole to the Eddington level. The main equation that we use to evolve such systems is the conservation of angular momentum. This is analogous to what is done for white dwarf binaries, for example, in Marsh et al. 2003. So in this equation we have that the variation of an angular momentum in the orbit is determined by two competing forces: the emission of gravitational waves, which tends to shrink the binary, and accretion, which tends to widen the binary if the donor is less massive than the accretor, as is the case in these systems. Another couple details that are important in the evolution of these systems is that the black hole is going to accrete angular momentum through the accreting material, and we use the general relativistic expressions for the angular momentum and the mass, the energy at the ISCO, the innermost stable circular orbit. And for the white dwarf, we assume that the white dwarf is tidally locked, so always facing the black hole during the orbit. This is a reasonable assumption for these systems because the synchronization timescale is going to go like the mass ratio squared, and these are low mass ratio systems, so the synchronization is going to be relatively fast. For the white dwarf, for now, we also assume that its mass-radius relationship is determined by the zero temperature one, and I will come back to this assumption later. So using this equation I just showed you and a few more assumptions on the accretion, the mass loss by the white dwarf, we can compute the evolution over time of all the relevant quantities for the binary. For example, on the top left, you can see the separation widening the binary over time, which means that the accretion force is dominating over gravitational wave emission. And accordingly, the frequency of the gravitational wave is decreasing over time. This is the opposite behavior compared to binaries seen by LIGO, where the frequency is growing instead. On the bottom left, you can see the accretion rate onto the black hole, and you can see the capping at the Huntington level that I mentioned before, and the fact that accretion is strongest at the beginning of the evolution. So right after Roche lobe filling for the binary. And finally, on the bottom right, you can see the mass of the white dwarf, the donor, which is decreasing over time and going below 0.1 solar masses. The later phase of the evolution of all these quantities is characterized by a sort of equilibrium defined by the derivative of the radius of the white dwarf being equal to the derivative of the Roche lobe radius. And it's exactly this equilibrium phase that allows us to, and other authors in the literature, to identify some interesting relations in the evolutionary tracks of these binaries. This was known already for white dwarf binaries, where, for example, in Breivik et al. And in 2018 and other references, a relation between the mass of the white dwarf and the frequency of the gravitational wave was identified independently on the mass of the accretor and the initial conditions for the binary. This is, of course, an extremely interesting relation for gravitational wave observations, because measuring the frequency, we can measure the instantaneous mass of the white dwarf. However, this is not the whole story for white dwarf black hole binaries, because we were able to identify a new relation which involves this time the derivative of the frequency of the gravitational wave and the mass of the black hole, so the accretor. This new relation comes about thanks to the mass ratio in the system, and thanks to the fact that the black hole will not have a tidal field and will therefore, and we can therefore neglect completely, abandon completely tidal forces in the binary. For white dwarf systems, on the other hand, this relation or some modification of this relation would only hold if tidal interactions are sufficiently weak, but this cannot be assumed in general. So this new relation will allow us to measure also the black hole mass from gravitational wave signals if f dot is measured sufficiently well. And let me show you this for one example system. So let's imagine to measure the gravitational wave signal from a white dwarf black hole located at a luminosity distance of 10 kiloparsecs. And we approximated the gravitational wave signal with this expression above, which is reasonable for such quasi-monochromatic signals. And you can see that for this system we have in mind f naught and f naught dot, these two parameters in our parameterization, are measured extremely well to the level of 10 to the minus 16 for f naught dot and 10 to the minus 8 Hertz for f naught. And using the evolutionary track relations that I just showed you, we can use these measurements to infer the masses of the two components. And again, this was not possible before for white dwarf binaries unless tidal interactions were assumed to be low. So you can see that the two binary masses are inferred completely from gravitational waves observations alone, and that the true value in red lies within the 2 sigma contour in this case. Again, for white dwarf binaries, the identification of the two masses would have required electromagnetic observations, for example, from the Gaia mission. And you can see also that the constraint on the black hole mass is sufficiently tight that we can cleanly say that this is a black hole and not some other star. The only potential caveat to what I've shown you so far is the fact that the white dwarf is not truly at zero temperature white dwarf. This is because the accretion disk around the black hole is illuminating the star to a temperature that we estimate to be around 10 to the 6 or 10 to the 5 Kelvin. So we think that the zero temperature analytical mass-radius relationship should be substituted by some numerical cooling sequences, for example by the Fontaine et al. 2001 simulations. Really, this temperature, illumination temperature, is not necessarily going to spoil all our results because this is still a lower temperature than the core temperature for hot white dwarfs that are observed in the galaxy. But this nonetheless needs to be tested. And this opens the possibility to test potentially the effect of illumination using gravitational wave and potentially a combination of electromagnetic signals. So to conclude, we believe that white dwarf black hole binaries are going to be another exciting target for the LISA mission, and that if illumination doesn't spoil our predictions, then both masses in the binary will be inferable by gravitational waves alone. While, as I mentioned before, for white dwarf binaries, Gaia mission data, for example, might have been needed for such a measurement. Of course, white dwarf black hole binaries are also interesting electromagnetic targets per se if LISA can identify their position in the sky. This could be an interesting target, for example, for Athena if it's flying at the same time as LISA, and this would, of course, be X-ray binaries. So thank you for your attention. Thank you for listening, and if you have any questions you can contact me. You can use the channels provided by the LISA Symposium, or you can ask your questions during the relevant discussion session. Thank you.